All right, welcome back, everyone. So we were talking about this. So in this graph, we are showing the rate of the reaction versus time. Yeah, reaction rate versus time. So when the reaction goes on, the forward reaction rate will be decreasing, and the reverse reaction rate will be increasing. And at one point, let's say that is T1, we will reach an equilibrium point, yeah, where the rate of the forward and the rate of the reverse will be equal here, yeah. Forward rate equal to reverse rate. When forward rate equal to reverse rate, then we call this as an equilibrium. And the point where it starts is an equilibrium point. Okay? Is it clear? Okay. You can write this graph in your notebook. And when you have a question, please ask while you are drawing the graph. Finish? All right. This is the first point, guys. The first point is the rate of the forward will be equal to the rate of the reverse reaction when you want to reach an equilibrium. The second point is this. All right. We have another graph here. This graph now telling you the concentration versus time. So it's different from the previous graph. In previous graph, we have reaction rate to the time. In here, concentration versus the time. Okay? In a forward reaction, where the concentration of the reactant will decrease. In forward reaction, the concentration of reactant will decrease. As you can see here, H2 or I2 is the reactant, it is decreasing. And the concentration of the product is increasing in a reaction, isn't it? In a reaction, the concentration of reactant will be decreasing because it goes to the product. And at the same time, the concentration of product is increasing. At one point, which is we call as the equilibrium point, the concentration of both reactant and product will become a constant. Here, constant, yeah. Constant is shown by the graph, which is right straight line, yeah. The graph that become a straight line like this, it is showing you that the reaction become constant. So what is interesting here? When it is become constant, it doesn't mean that it will have the same concentration. As you can see here, The concentration of reactant at equilibrium, so this area is equilibrium after the equilibrium point. This is the equilibrium point, yeah. The concentration of the reactant and the concentration of product are not the same. This is the point. Their concentration are not the same, but both of them will become constant. Both concentration become constant, but become constant, it doesn't mean equal. It doesn't mean must be equal. It's not necessary to become equal, the concentration of reactant and product, but they must be constant. They must be constant. All right. Please try to write also this one in your notebook and think about this. If you have a question, please ask. Any question? No? Can we move? Right. Next one is the fundamental of dynamic equilibrium. Like I told you that an equilibrium is a dynamic process. So this is very important. Dynamic process, it means that it is not a static, which is not moving. No, it is moving, but it is continuously moving. Yeah, like you are biking your bicycle, to make its balance, you have to continuously moving. So it's the same like that one, equilibrium. To make it equilibrium, it must be dynamic. It must be continuously moving. And the consequence of that continuous moving, you will not see any changing. No visible changing can you see, because when you dig a hole, at the same time you close it. So you will not see the hole, like gali lubang tutup lubang, yeah? You dig hole, you close it. So you will not see the hole, you will not see the changing actually. And the reaction must be spontaneous. It's reacted by itself to the forward and to the reverse. Yeah, it must be reacting itself, spontaneous, and it must be continuously, like the analogy in bicycle. To make it balanced, it must be continuously going forward and reverse at the same rate, yeah, at the same speed. It must be continuously. And one more thing that I have to say, that it must be in a closed system, in equilibrium. So you can have an equilibrium reaction if the reaction is in a closed system. If in an open system, you will not see an equilibrium there. So it must be closed. And the temperature must be kept constant to the equilibrium. If the temperature is changing, of course, the equilibrium also will be changing. Okay? So this is important things. You can write also this one in a notebook. Please ask if you have any question. yoga is sitting in the classroom. Right. What things that we can't see any visible change, sir? What do you mean, Rizky? I couldn't get your question. Can you say bahasa?
Di sini kan dituliskan kita tidak dapat melihat, tidak menunjukkan sesuatu perubahan.
Yes.
Nah di sini yang dimaksudkan itu seperti apa, Mister? Kayak perubahan apa gitu yang bisa kita lihat?
Concentration.
Concentration. Okay.
The concentration not change.
Okay, Mister. Thank you.
You will not see the changing in concentration. So it's look like the concentration is constant, but actually it's not constant, static constant ya. Kalau constant itu tidak mesti harus static, but constant also can be dynamic because of the continuously process. So it's look like no changing, but actually they are changing in same speed for forward and reverse, actually like that. All right, let's continue. Okay, I keep that one. Now we come to the, let's see, that's in the equation part. Okay, in equation part, we're going to getting help from the rate law. Yeah, we learned about the rate law before. Yeah, I think everybody remember this rate law. In rate law, we have equilibrium. We have a rate constant, isn't it? We learn about rate constant. The K, yeah, the one which is K. In equilibrium, also we have that constant, but now the constant is changing the name, not rate constant, but it is equilibrium constant. And also we have expression like a rate law. In rate law, we express the rate in the equation. For equilibrium, also we can express the equilibrium in an expression. Now we are going to see how we can write the equilibrium constant and equilibrium expression. Actually, it's coming from the rate also, coming from the rate law and rate constant. Yeah. For example, if I have a reaction like this, A plus B plus C plus D with coefficient small a, small b, small c, small d. And please imagine that this reaction is one-step reaction. What does it mean, one-step reaction? No mechanism, yeah? No mechanism in the reaction, is one-step reaction. And we learned that from the rate law and rate constant, when it is one-step reaction, the order will be what?
The coefficient.
Yes, the order will be the coefficient if it's one-step reaction. So we are going to think that this is a one-step reaction, then we are going to take the order of the rate from the coefficient. So I can write down the rate forward. Rate forward is from reactant to the product, rate forward. Rate forward is equal to Kf, which is the rate constant for the forward, time concentration of A to the power of A, concentration of B to the power of B, rate forward. And I can also write down the rate reverse, which is the reverse from product to the reactant. So from product to the reactant, so the product now will be the reactant and the reactant will be the product. So that's why I will write the rate reaction for reverse is equal to K reverse time concentration of C to the power C time concentration of D to the power of D. Okay, is it clear how to write the rate forward and rate reverse? The same like you are writing the rate flow and rate constant, yeah, at one-step reaction. Okay, If it is clear now, I will make the condition equilibrium. If I know the rate, the equilibrium means that the rate forward will be equal to the rate reverse. Rate forward equal to the rate reverse. Put this equation into this rate forward equal to rate reverse, and you will get this equation, Kf a to the power a times b to the power b equal to kr c to the power c d to the power d. Yeah, and then this equation, I'm going to rearrange it. I'm going to playing with mathematical calculation a little bit. What I'm doing, I will put the constant, the forward constant and the reverse constant at the same side, and the other side is for the concentration. So when I arrange the equation, I will get that Kf over Kr, where the constant is at the same side, equal to c to the power c d to the power d over a to the power a b to the power b. Okay. Now what I got, two constant at the same side here, k forward over k reverse, red constant of forward over red constant of reverse. This will become a new constant, and new constant is called as a kc. What is kc? Kc is equilibrium constant in terms of concentration. In terms of concentration. Okay? So K, now it is capital K. Capital K to the C is mean as equilibrium constant in terms of concentration. It's coming from rate constant of forward over rate constant of reverse. And at the other side, we will see that the concentration of C to the power C, D to the power D over concentration of A to the power A, B to the power B. We know that the C and D in the reaction is the product and A and B is the reactant. So in general, I can say like this. Kc is concentration of product over concentration of reactant. Of course, we have also will have the power. The power will be the C, small c and small d, small a and small b. What is this? The power will be the
Coefficient.
very good.
Coefficient.
All right, the power will be the coefficient. So this is the equilibrium constant and equilibrium expression. You can write this one in your notebook. If you have any question, please ask. If there is something which is not clear, is it clear? Everything is gonna be okay or not? Yes, when you are writing, please try to understand. If you have a question, please ask. Can we move? All right, let's move. Here are some example of how to write the rate, not rate, yeah, equilibrium constant expression. What thing that you have to remember again, solid and liquid are not included in the Kc expression. It is the same like in the rate law, yeah. In rate law, solid and liquid also not written, isn't it? We only written the gas and aqueous one. So it's the same time, the same things like in the rate law for Kc expression also, the solid and the liquid is not written, are not included in Kc expression. So for example, if I have a reaction like this, N2O4 in equilibrium, 2NO2, how to write the Kc is very easy. Kc, it must be equal here. Kc is equal to, first you're going to write down the product, NO2, the concentration of product, to the power of the coefficient, to the power of 2, over concentration of the reactant, to the power of 1. For the second example here, because this is solid, it's not written, this is also solid, not written. So in the product, we don't have any concentration. So let's write this one is constant, equal to the reactant, we have only O2 remaining, O2 to the power of 1. For the C, now, the product is this one, N2, Kc is equal to concentration of N2 times concentration of H2 to the power of 3, because this is coefficient 3, over concentration of NH3 to the power of 2, because we have coefficient 2 here. And for part D, AgCl solid is not written. So in the product, we don't have any concentration, just write 1 over concentration of Ag times concentration of Cl. So this is the Kc expression. This is how you write the Kc expression in a reaction. It's quite easy, not very difficult. Just you will remember product over reactant, concentration of product, all the product over the concentration of all the reactant, but you will take only the gas and the aqueous one. For solid and liquid, you will not include it in the Kc, and the power will be the coefficient. That's it. All right, finish? All right.
Yes, sir.
Okay, let's continue to the example. Now, can you write this question? And then after that, we're going to solve it. All right, finish. Okay, if is it finished now, I'm going to show you how to solve this kind of problem. There's a trick here in solving an equilibrium equation. What should you do to solve an equilibrium equation? First, you're going to write the reaction x2 plus 2y2 in equilibrium, this symbol, 2xy. And after that, we are going to write the matrix for this one, I, R, E. What is I, R, E? I is initial, R is reaction, E is equilibrium. Initial, reaction, equilibrium. Now, look at the information from the question. The initial amount of X2 and Y2 gas present in a 2-liter container are 2 mole and 6 mole. So we have the initial X2 and Y2, which is 2 mole and 6 mole. I could write here 2 here, 6 here, because it is initial. How about XY, the product? Of course, initially there will be no product, so 0. The product initially always be 0 because the product will happen after the reaction. When it is initial, not happening the reaction or not starting the reaction, then there will be no product. Okay, and then the amount of XY2 is 1 mole at equilibrium. So I could write here at equilibrium XY2, this is XY2, yeah. XY2 at equilibrium, it is 1 mole here. So this metric showing you that at equilibrium, XY2 is 1 mole. Now the question is, what is the value of constant Kc? Constant Kc can be found by concentration of XY2, I'm writing the Kc expression, to the square because it is coefficient is 2, over concentration of x2 to the power of 1 times concentration of y2 to the power of square also. Now, the one that I'm going to write in Kc, because Kc is equilibrium constant, the one that we are going to take the value in Kc is the one which is equilibrium. So the value at the end here. So you have to know what is the value of x2, y2, and xy2 at the equilibrium here. Then you will put it into this equation. The problem here, how to find the equilibrium value for x2 and y2. For y2, it is already given in the equation, it is 1. But for x2 and y2, it is not given, so you have to find it. How to find it? It is very easy because equilibrium is the sum of the I and R. So when you sum I with R, you will get E. 2 plus blah, 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 you get the equilibrium. 6 plus blah, 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 you get the equilibrium. 0 plus blah, 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 you will get 1. So when you sum I with R, you will get E. And what things that important that we know that in the reactant, the reaction, the mole number of the reactant will always be decreasing. So the reactant will be minus. The reactant will be minus, and the product, the mole number of the product will always be positive. So in the reactant, the value always be minus, and the product, the value always be positive. So from here, I can get that what will be the value of the reaction for the XY2 here? If initial 0, equilibrium 1, so the R will be plus. It must be plus 1, right? To make it 1, it must be plus 1 here in the R of XY2. Now, it is very easy. If one of the R is knowing, if you know already one of the R, for example, here XY2 is already known here, plus 1. Then you can find the other value by looking at the ratio of the coefficient. Now look at the ratio of coefficient 2, 2, 1, 2xy2, 2y2, and 1x2. So the ratio of the reaction also will be equal to the ratio of the coefficient. So if it is 1 here, y2 also will be 1, but now it is minus 1. And x2 must be x2 0.5.
5.
Yeah, because the ratio is 2 to 1, so 1, 1, 0.5. So if you know already the R, then it's easy to find the E. Now 6 minus 5 is 6 plus minus 1, it is 5. 2 plus minus 0.5, it is 1.5. So you will get this value. And what is the unit of this one?
Mole.
Must be mole, because we are using mole here, 2 mole and 6 mole and 1 mole. So the unit is mole. But look at here, in the expression, it is in concentration. So you have to convert this mole into concentration. So in terms of concentration, mole will be divided by volume. And the volume of the container is given as 2 here. So I can write here xy2, the equilibrium is 1 over 2 square, because we have square here, equal to, sorry, not equal, I'm sorry, why it is equal? It must be over 1 over 2 square over x2. x2 here is 1.5. 1.5 to the divided by 2, because we have to change it into concentration, times y2. y2 is 5 moles. 5 divided by 2 square. Now you can calculate this one. What will be the value? Can you calculate, please? Yes, what's the value? I can write like this, 1 over 2 is 0.5, yeah, 0.5 square over is 0.75 times 5 over 2, 2.5 square. Yeah, you have to calculate this one to get the last answer. Some of your friends writing the answer, 0.053, good, very good. It is 0, yes, 0.053 is the answer. So this Kc value is 0.053. Right, do you have any question, guys?
Sir, I wanna ask,
Please.
why the Kc must be divided by 2? I still don't understand.
Okay, you mean this one? Why it must be divided by 2?
Yes.
Because what you got the value from the matrix here, the value is small, isn't it? But here is concentration. The one which is in Kc is concentration. So how to convert the mole into concentration? This formula. Concentration or molarity is equal to mole over volume. So the mole, all of the mole here, you have to convert it into concentration by divided by volume. Okay,